Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff, the real good stuff. This is the AAS Author Series. And I am super pleased to have Gibor Basri with us today. Hello, Gibor.
Hi, nice to be here.
Good. How you doing today? All things considered.
Yeah. Well, the sheltering in place is working pretty well for me here.
Where is here for you? Where are you at?
I'm in Berkeley, California.
Berkeley. All right. Very good.
The Bay Area has been doing pretty well in terms of the COVID emergency, and so there's a lot of nice weather and nice hiking, and so been doing all right.
All right. Very good. Looks like you have some nice astronomy books on your bookshelf back there. I see something that looks like a red giant back there. What do you got?
Yeah, I don't think there's any red giants there. There's actually well, here, I'll show you.
Yeah, let's take a look. Brown dwarf.
Well, a chapter in.
Well, they colored a brown dwarf red. You know, what am I to say?
And this book is a little paperback book that the Lawrence Hall of Science did for kids.
Oh, cool!
And it talks about the Kepler mission, and I talk about stuff in here.
Oh, very cool.
So that's kind of fun too.
Well, we will absolutely have to put a link to that in the video description down below. We'll put a link to that in case anybody's interested in that for their kids. Or if you like brown dwarfs, we can put a link into the brown dwarf stuff as well. So speaking of brown dwarfs, in stars at the lower end of the main sequence, what do you like to do for research?
Well, actually, when I came to Berkeley, 40 years ago, amazingly enough, one of the folks here, Frank Shu, who actually was the president of AAS in the 90s, told me that if I wanted to really have fun my whole career, I should do some change of topics every decade or so. And so I worked on T-Tauri stars kind of for the first decade. I worked on brown dwarfs for the second decade, and then I had a sojourn with red dwarfs, and then in the last, 12 years or so, I've been working on the Kepler mission. The thing that ties them all together is stellar activity, stellar magnetic activity.
There we go.
So I haven't done any actual work on brown dwarfs for about a decade. I've been working on photometric data from Kepler.
Well, I know what my last question is going to be to you. What will be your next trick in the fifth decade?
Well, I don't know.
We'll find out. But now that you mentioned, let's go ahead and get rolling. And we are going to have a discussion of the calibration of differential light curves for physical analysis of sunspots. And Gibor, take it away.
Well, as I just said, the last decade or so, I've been working on Kepler data. I got involved with the mission because I thought this would be interesting, and also because people were quite worried about whether star spots were going to create a real problem for finding planetary transits. And it was in the early 90s, before actually exoplanets had been even discovered. There was a committee convened because Bill Barucki was really pushing the Kepler concept, and NASA Ames wasn't sure it was a good idea. So I was on this committee, and I was there to assess the question of whether star spots were going to be a problem for this mission. And I concluded that they really weren't, because the timescales are pretty different. But it also piqued my interest, and I thought, wow, well, if one did a mission like this, you sure would learn a lot about stellar photometric variability, in addition to being probably successful on the exoplanet search. Cool. So I got more and more involved with that effort, and ended up as a co-investigator on the final mission that was accepted by NASA.
Congratulations.
And so I have basically looked after the question of what are we learning from star spots? What can we learn? and making sure that the mission pipeline didn't completely wipe out star spots, which was their original intention.
Oh.
They were going to just publish flat curves which only showed planetary transits, and I was one of the folks who pushed for let's not do that until after the pipeline is usable by stellar astrophysicists.
Absolutely.
So then, but then, you know, we began working on this science, and I'd say it's been a slow realization that although the light curves are tremendous, you know, essentially 4 years of continuous data with very high photometric precision, they tell us less than we think so far about actual star spots. And the problem that I've come to realize is the light curve is really just telling you how bright the entire hemisphere of the star that's facing you is at any given time. And it turns out to be, you know, a degenerate and difficult to disentangle problem to learn too much more than that. And so in particular, this paper, you know, I've been thinking hard about, I mean, we all knew, I think, although a lot of people didn't get hung up on it, we all knew that the data as given by Kepler is missing one very important part to it, which is the absolute flux from the star. So the Kepler data is differential, and so that's the title of the paper, Calibration of Differential Light Curves for Physical Analysis of Star Spots. That's the gap there is between the differential and the physical analysis.
Okay.
Because it matters what the absolute brightness of the star is doing, and it especially matters because of the way Kepler data is reduced. Essentially, you have the differential changes in light over 1/4, and even that is not pristine. So they essentially take out secular changes that are on the timescales of a month or so. So those are kind of removed ahead of time, and then the quarters, because they don't do absolute flux, the quarters are medianed together. So you get a curve that is that looks, you know, kind of flat over time. It goes up and down above its median, and it's missing the sort of data, the changes that are occurring on timescales of a few weeks, and it's also missing the relationship between quarter to quarter. Okay. So that was the motivation for. So now, you know, so if you want to say, let's say, tell how much of the star is covered by spots, you kind of need to know how bright the star is when it doesn't have spots. And another thing that becomes clear as soon as you look at Kepler data is it's not as though most stars have long flat segments and then dips where a spot occurs. They almost all just kind of go up and down.
Yeah.
And so that means you're not seeing unspotted star much of the time. And then you're not sure, you know, how much below the unspotted level you sit.
Oh, right. Yeah.
So that's, you know, if you don't know that, you don't really know how much spotting you have. So that's part of the purpose of this paper, is to sort of talk about that.
Yeah, put some light on that. What are the issues with that?
Yeah, so I mean, that's maybe a good introduction to the point here. So why don't we go to figure 1?
Let's take a look. Oh, I love the title of that section. What is the problem?
What is the problem?
Right,
why am I even doing this?
Just elucidated that. Okay, so here we got KIC 59, 51, 7.
Yeah, some random solar type star.
Telephone number.
You know, now this is, you know, significantly more active than the sun itself, as you'll see in a little while. But these are the kind of light curves that one thinks contain the most information. And just to be more explicit about what we'd really like to learn from this, now that, you know, I mean, the Kepler sample is sort of 100,000 stars with
Yeah.
with you know, Fourier light curves. So we'd love to be able to infer from that, for example, how does spot lifetime depend on stellar parameters? You know, do
Yep.
spots live as long on 6,000 degree stars as on 5,000 degree stars? Does it change with the rotation rate of the star, which changes the level of magnetic activity?
Right.
Kind of a holy grail here. Can we infer differential rotations
Ooh.
from these light curves?
Right.
And you can see that the light curve there shows what look like some sort of beating patterns in it.
Yeah.
And you know, that could be more and less spot coverage. It could be differential rotation because if you have sort of the same spots, but they change positions with respect to each other, they will, when more of them are collected on one hemisphere of the star, you'll get a larger variation over rotation. And when they're sort of spread more evenly around the star, you'll get a smaller variation.
The blue curve is the envelope almost?
Well, I'll come to those curves in a minute.
Okay.
So the first question, as I said, is, you know, we don't know what the unspotted level of the star is. And if you want to infer coverage, you need to do something about that. And so the green line in the upper plot is what actually most people do most of the time. They look at the light curve, they say, well, let's pretend that, you know, when the star is brightest, it's the least spotted.
Okay.
And we'll set the unspotted level somewhere there. I mean, I could have put it above all the points too.
Right.
But because of the way Kepler data is reduced, you're in trouble already, because there are 16 quarters of data on that curve. And they've been, you know, remedianed, and they've had secular variations removed. And so, yes, the star is more variable in the last part of the curve there. And but if I set the unspotted level there, I'm kind of making the assumption that all the rest of the curve can be referenced to that same calibration.
Right.
And I'm arguing in the paper that's, well, it's not usually a good idea. Sometimes it is, you'll see. And unfortunately, I mean, the bottom line of the paper is we don't know enough about what the stars are doing to be able to trust any of this, basically.
Okay.
So, you know, if you take the green curve as the unspotted level and just apply it to the Kepler light curve, the coverage that you infer, which is the bottom plot there, is fairly flat, because most of the curve is, you know, sort of a certain level below that green line.
Right.
And you can see the coverage changes over near the latter part, as you would expect, since the amplitude is changing. But that would, you would infer from that the star was usually very covered with spots. That's why it was so depressed most of the time.
Right.
And you know, and it must be very covered because there's not much variation going on, but the level is, you know, there's quite a deficit. If, on the other hand, you fit the envelope, as you pointed out, the blue curve tries to sort of fit the envelope of the points. You know, what would be the assumption there? Well, that the calibration is, you know, really bad on time scales, you know, longer than a week or two, and I should really just reset the level according to that.
Okay.
And of course, the coverage that you infer is, you know, much less. Basically, the deficit is much less. Although you still get a, you know, more coverage near the latter part of the light curve, just because that blue curve can't follow the wild variations of the light curve itself as much. So you infer there are more spots there where the amplitude is higher, but there usually aren't that many spots, because the blue curve is, you know, down near the black curve most of the time. And then the other two, the red and the brown, are basically just what time scale do I think I need to, you know, undo this differential calibration on.
Okay. All right.
And that, you know, that it turns out they give you kind of the three curves, the not green curves, kind of give you the same answer for most of this light curve, which is maybe interesting, maybe not. Anyway, that's just to set up. So what is the problem? The problem is, you know, we don't have absolute calibration, and then you really aren't sure what to do. That's the problem. All right, let's go to the next figure.
Okay. Slide on down. Figure 2, an active sun.
All right. So another practice that I try to do as much as I can is to refer back to the sun whenever I can. Whenever I'm talking about stellar magnetic activity, I first think to myself, and is the sun going to provide us information that we can't get on these other stars? Because with the sun, we know what's going on. We can see the whole thing. We have great spatial resolution, full wavelength coverage, full time coverage. We're good. And so whatever you're going to do with the stars, if you can do it with the sun too, then you can test whether your methods are at least work there.
Okay. Yes.
So in this case, the black curve is the absolutely calibrated light from the sun in a Kepler-like bandpass. It turns out people have been working. I just refereed a paper actually where they showed that the total solar irradiance is a pretty good proxy for the light that you get in, say, the Kepler bandpass.
Okay.
But I think what I did here was I took the Virgo data and used the green and the red filters and combined them to give me a pseudo Kepler bandpass. Those are narrowband filters, but I had also done work showing that basically works. And this latest paper really proves that it really works.
Cool.
So that's the output from the actual output from the sun. And then I Keplerize it. And what do I mean by Keplerizing? I mean divide it up into quarters, like Kepler does. Take out you know, a low order polynomial from those quarters, and then fix their medians so they're all the same.
Okay.
And that gives me the green curve there. So that's the black curve Keplerized looks like the green curve.
Yeah. Okay. Same colors. Okay. Yes.
I know it's hard to disentangle them because, you know, fortunately they all kind of look similar in this case.
No, I'm with you.
Now, as I said, the sun provides a real example where we're not guessing. So the blue curve here, you know, the dark blue curve, is the actual area of the visible disk of the sun that's covered by spots. That someone has gone, you know, day by day and measured how much spotting there is and calibrated the area.
Wow.
So that is the truth. That's the truth.
Right.
So the blue curve is actually the truth. The black curve, you know, rises up, but it has pretty much the same dips. The rise, I mean, actually it's falling from left to right. That is the effect of faculae on the sun. So
right.
Those are not spots, they're bright patches. And the more active the sun is, the brighter it gets due to those. And the spots cause sharp dips compared to the faculae because the faculae are spread out quite a bit more than the spots. And they also show up more at the limb. There are a number of differences. So spots still show up as dips in the sun, in the solar intensity. And the faculae kind of change the absolute level in the way that you see. And then I apply the same fitting methods to the light curves that I did in the figure 1 there to get the green curve and the red curve and so on. Now in this case, the sun, the Keplerized sun is pretty flat. It doesn't go through those wild gyrations like the curve did in the first figure, and so all the methods work reasonably well in that instance. If we can go to that's the active sun. Let's go to the next figure, which is the sun as it transitions from active to quiet, and then the bottom figure is quiet. Yeah, maybe have them both up at the same time. Okay, we can look at it. The transitional figure, you see a problem is starting to appear with the flat fit, the green fit there. As the sun gets very quiet, the fact that it had more of an amplitude on the left-hand side and less on the right is starting to cause a problem, the same kind of problem that we saw in the Kepler star.
Yes.
The red curve doesn't have as much of a problem, but it's not quite following the blue curve the way it was in the active sun. And then if you look at the bottom figure there, that's when the sun is really quiet. Now you can see that the truth curve, the blue curve, does show long flat segments. So there are significant times where there are no spots on the sun, but the intensity doesn't show that. So like with all the Kepler stars, it's always going up and down anyway. However, now that's not really due to the spots anymore. In the case of the sun, this is mostly a facular signal now. And interpreting it in terms of spot deficits gives you definitely the wrong answer. So all those curves are low. They all indicate coverage that isn't really there.
Not there. Right. Okay.
So the method definitely fails when stars are really quiet. In the case of Kepler, that's not as much of a problem because those stars, basically, mostly what you see is instrumental noise. And you probably don't interpret that as spots anyway, but
hopefully not.
Something to be wary of.
Yes.
Okay.
Wow.
I guess so that what that tells us is if stars are kind of like the active sun, then these different methods aren't going to fool you too much. If they're more active than quite a bit more active than the sun, like in figure 1, then you got a problem. And if they're less, if they don't have activity, you've got a different problem.
Right. One's above, one's below. So you're looking for the Goldilocks right in the middle.
Right. Now, the stars we're mostly interested in Kepler are more active. I mean, they're at least as active as the active sun, or more, because the other thing you need to know to go much further here is what is the rotation period of the star? You're going to interpret features as coming from spots being carried in and out of your view. You kind of need to know what the rotation period is. And so in the Kepler data, the stars that people were able to, and I worked on this, but they're the usual reference here is McQuillan et al., 2014.
Okay.
So they got periods for something like 34,000 stars, and they didn't get periods for something like 99,000 stars. And so those are kind of ignored, and most of them are probably quiet. So we're not going to try to get spot data from them anyway. Okay, let's go on to figure 3 or figure 5, I guess.
Do you recall how Quinlan et al. Got their rotation?
Oh boy, do I recall it. For the last year, I had set myself the task of doing better than they did.
Okay.
And trying to get periods for the stars that were too quiet for their method.
Okay.
And I have to say at this moment that I have a more respect for what they did. I haven't really been able to, well, I should say I have been able to get apparent periods for quieter stars, but I haven't been able to fully trust what I'm getting compared with what they got when they did get something, my method, which is kind of an extension of their method anyway. There's about 10% of the stars where I get half the period they get. Some of those, I'm pretty sure I'm right. It's not surprising that if they didn't get them all right. But I'm still struggling with, my method cannot rely on, knowing whether it matches theirs or not and then fixing it.
Yep, right.
For all the stars they didn't do. So I'm still working on that. But just to answer your question briefly, the essential method is an autocorrelation method. So you just take the light curve, you slide it against itself,
Mm-hmm.
And if there's a periodicity in there, the correlation will be stronger every period or so.
Correct. Okay, got it.
And, so I'm taking that and I'm saying, okay, and I can believe it more if that correlation sticks for, you know, a few phase shifts. So in other words, if the spacing of the periods stays fairly fixed for 4 or 5 you know, phases out, then I'm pretty confident I have a period here and it's kind of fixed. The difficulty, and this goes back to the paper I wrote before this one we're talking about, difficulty is that sometimes stars only give you 1 dip per period. And that's if, you know, if one hemisphere really is darker than the other hemisphere, I'm going to get a single feature per rotation.
Yes.
But if the spot pattern is complicated enough, I might get 2 features per rotation. It turns out to be hard to get many more than 3 features per rotation because your light curve really only resolves the whole hemisphere. So it's actually difficult to get spot configurations that would give you 3 or 4 dips within 1 rotation period. And that paper talks about all that. And I've been running tons of spot models, some of which are in this paper, to understand what that's all about. But the problem when you get 2 dips per rotation, if you get that a lot, you're going to think the rotation period's half of what it is.
Mm-hmm.
So that's essentially the place where I'm struggling still.
Yep.
I can tell. I mean, I know in the models when it's a half period, but is the method really able to tell the difference? That's the trick.
Right. It's predictive.
Okay. Well, yeah. So this paper we're talking about had kind of 2 main purposes. One was the one we're talking about, how to sort of calibrate the amount of deficit that you're seeing compared with the unspotted star. And the other thing I was worried about is, and are faculae really causing a problem here? And so the listeners may or may not know that stars exhibit 2 kinds of behavior depending on how active they are. So more active stars, really active stars, if you measure the magnetic activity with some other proxy like X-rays or calcium-2 or something, then the more active stars in that proxy will tend to be darker when they're more active. That is to say, there'll be more spots on the star when you see these other signs of magnetic activity, and the star gets darker.
Yep.
But you just saw the sun, when it's more active, it's actually brighter. And that's because the spots effect is overwhelmed by the effect of the faculae. And so there's a switch between stars that get brighter as they get more active or get darker as they get more active. Okay. And the sun is actually right in between, as you kind of saw already. So this figure 5 shows the brightness compared with the variability. So the variability is just the amplitude of the spot signal there, basically. And the brightness would be the absolute brightness. And for the active sun, that's the green diamonds there. You can see that the variability is higher when the brightness is lower. So that there the sun is darker when it's more variable.
Okay. Yes.
Whereas the transitional sun, that dark blue line, has the other slope. There it definitely goes brighter as you get more variability. Mm-hmm. And we understand why this happens. It is the interplay between faculae and spots. So that's just to introduce this topic here. Now the question is, what about the Kepler stars? So the other part of this paper is, it turned out that there was a prior paper by Montet et al. In which they said they actually did get the absolute brightnesses of the Kepler stars only once a month, but that's better than nothing.
Absolutely.
And so can we see the facular signal in those? That was the other part of this paper.
Okay.
All right, so let's move on. I think we go back to the first topic here. Right. So as I said, I've been running actually tens of thousands of spot models and trying to understand their light curves. But in this case, I was also trying to understand if I take that light curve from the model and I Keplerize it, same way I did with the sun. Right, so I divide it up into quarters. I take out the low ordered polynomial. I median the quarters, and then I try to see, the resulting light curve. How does that behave compared to the real light curve? And then how do my fitting methods do in terms of what's the real coverage on the star? Because in all these models, of course, I also know what the real coverage is. So in these curves, the black curve is the actual model, so in absolute flux.
Okay.
The unspotted star is always at unity. And then let's see, the Keplerized curves, if you can squeeze out a little bit so we can read the whole legend. Yeah, so each of the other curves are after Keplerization and then using one of the methods that we talked about in figure 1. So for example, the panel A there, and that's a case where there is differential rotation and no evolution. So whatever spots are there, they start wherever they got put to begin with. And the only thing they do is they differentially rotate. So the pole rotates more slowly than the equator, and in between follows the sine law. And so they shift configuration slowly, but they're not changing their sizes at all. And so the pattern that you see there is just due to differential rotation. And
yes,
the green one is if I just use that flat, if I take the Keplerized light curve, I set the unspotted level at the brightest point and just assume that applies to everything, then I get this green curve, which is wrong for most of it, and that's because the star had a bigger amplitude when the spots managed to collect on one side more, and then I took that amplitude as the unspotted curve, but the Keplerization, basically did damage since I didn't know what the absolute flux was in all the quarters. It suppressed the quarters where the spots were more spread around. So that's what kind of happened with the figure 1 as well. On the other hand, in the bottom left, the panel F there, it's got the same differential rotation, but now the spots have a lifetime of 60 days.
Right.
And so they grow for 30 days and then they decay for 30 days, just linearly.
Okay. Okay.
And that that destroys the pattern that you saw in the first panel. And it turns out that all the methods work pretty well in that case. In other words, the coverage on the star behaves in such a way that Keplerizing doesn't really do a lot of damage to it. And it works there. And then there are other examples there. We don't need to go through them all, but I was just looking at, when does this work and when does this not work?
Right, right. Yep.
Okay, let's go to the next figure.
Cool.
And this is similar to the previous figure, except the top 2 panels are actual Kepler data, and the bottom 2 panels are models that I picked out that looked kind of like the Kepler data, just to show that these models are reasonable, the parameters that I'm using and so on. But once again, I find cases where each method works or it doesn't work, and that's discussed. I'm not gonna
Yeah, that's fine.
spend the time here, but that's what's going on here basically. You're looking at various cases, and sometimes it works and sometimes it doesn't work.
Do you get a sense of the fraction of what fraction of the time it works and what fraction?
Well, it's not so much a matter of fraction. It's a matter of which parameters you're using. you know, we don't know whether it's working or not in the Kepler data, and with the models, it works for certain kinds of models and not for other kinds of models. The bottom line in this paper was, okay, but usually the methods, some fail and some don't in any given case. And there are some cases where they all kind of work. And maybe for those cases, you can actually believe what you're doing. If it doesn't seem to matter too much which way you do it, then you're probably getting a reasonable answer. That's sort of the punchline to this whole thing here. It's like under most circumstances, it's pretty confusing and you can't really tell. But if you apply, you know, all three methods and they all give you the same answer, that seems like a reasonable to proceed.
Yep.
Okay.
Cool.
All right, let's move on.
Okay. Two more.
Yeah, these are just two more examples.
Yep.
Okay. So now here now I tried to figure out whether faculae are causing a problem, or whether we can even tell if we see them. So the blue asterisks are the supposed absolute flux points for these stars from the Kepler data from the Montet et al. Paper.
Okay.
And what they did there was every month or so, Kepler had to rotate off the field, point its high gain antenna at the Earth, and squirt the last month's data down. And before they did that, they would take a full frame image and squirt that down too. So most of the Kepler data was done with little postage stamps around the target stars, and you only downloaded those pixels. And that's part of the reason that there's no absolute calibration. But once a month, they would actually download the entire, you know, I think 100 million pixels. And then you could do absolute calibration with, you know, standard stars around. And that's what Montet et al. Did.
Got it.
I thought, oh, great, you know. So at least once a month we have an absolute calibration. We also know what the half-hour data is doing. So you can tell if you're at the bottom of a deep dip or at the top of a peak, or you know where you are when this full frame image gets taken. And so you know how to put those two together. And can we calibrate the Kepler light curves at least sort of on a monthly scale that way? I was disappointed to find that it didn't look like that works, and it made me wonder how good these absolute calibrations are. So like looking at the top at panel A there, it's a bright star. There's no problem with noise, and it's not doing much. It's a quiet star, and yet the absolute flux changed quite significantly during this time period. So the blue points are the absolute flux. The black point is the star. If I just force it to just very generally follow the blue points, you know, with a low order polynomial, then you see this big dip in absolute flux, you know, around day 1300, and there's no indication in the spot curve that anything went on there, and that makes me wonder about these calibrations. So you can see for all of these cases, it's not clear that the star is doing what the absolute flux suggests. So the black curve in each case is this sort of low order calibration to the blue points. So that should be the real star with the high time resolution amplitude on top of it. And so, but I just said, okay, let's just ask the basic question, which Montet et al. had asked and had thought they saw evidence for these two kinds of stars. One kind where when the star gets fainter, the amplitude gets bigger, and the other kind where the amplitude gets smaller when the star gets fainter. And so they said they saw this, and they went on about at what Rossby number does this occur and so on. I said, oh, well, okay, great. let's see if I believe this. So we can probably move to the next figure.
Okay.
Let's bypass that one. That's just about noise. Okay, here, this one.
And we'll back that down a little bit. I'll
Yeah.
get that straightened out.
So in the upper plot, I just have 5 examples of stars where, you know, I get the relative variability from the high time resolution light curve, and I get the relative absolute brightness from the Montet brightness curves. And you just, like I did with the sun, you just plot the one against the other. And, you know, sometimes you see a kind of an upward slope to the right, and sometimes you see a downward slope. And those would be the stars that are correlated or anti-correlated between variability and brightness.
Yes.
Okay, so the lower plot then shows how they all kind of fall out here.
That's Pearson coefficient.
And how well correlated they are as well.
Right.
And so indeed we see the 2 kinds, the reds and the blues, basically, that are get brighter with variability getting larger, or get brighter with variability getting smaller. The ones that are red, I think, are facular dominated, essentially, and the ones that are blue are spot dominated.
Yep.
And it's not surprising that most of them are spot dominated, because we have this observational bias that we can get rotation periods a lot more easily if the spots are giving us a nice signal. And those are the more active stars, and they should be the blue ones. So that all worked. I looked at how active they were and so on, and that all made sense. And the ones that are green in that plot are ones where Montet et al. Actually thought they saw a brightness cycle over time, and those are all in the blue arena as well. But as you saw in figure 1, you can get a brightness cycle with no actual change in spot coverage. They just have to collect on one side of the star or be spread around. So that's another thing that I keep trying to warn folks about.
Be careful.
Be careful. Okay, I don't even remember what the next one is, but
we can 12 if you like.
Oh yeah, right. So now let's see if this makes sense. So we know which ones are facular, which ones are spot dominated. We also know that magnetic activity depends on rotation period. We have the periods for all these stars. Does it all hang together? And here I thought, you know, I'm a little concerned about whether this all hangs together or not.
Okay.
The upper plot, the yellow diamonds are the 3 solar cases that I did: the active, the quiet, and the transitional.
Okay.
So that's where they lie on there. So the active one just makes it below the line into the blue, and the other 2 are definitely facular for the sun. And then you see the stars that we derived this way. And there are a couple of things that bothered me about this plot. One is that the facular domination didn't look like it cared about rotation period. I would have expected the stars that were facular to be the slow rotators, less active stars. But there were a bunch of cases where it was pretty fast rotation period, but they showed up with clear facular correlations. And I went in detail and looked at the light curves, and, you know, do I really think this is something weird going on? But no, that's what they did. And that made me suspicious about whether we're really seeing a facular signal here, or maybe we're seeing, you know, 2 different reasons why stars get brighter when they get more, you know, less active, or more active in this case. And I suggested, well, okay, you know, if the ones on the right are facular, then the ones on the left would have to be something like microflaring or something, you know, some other way to make the star bright.
Yeah.
It's really active. That would be the only way you could get that. And then the other thing is the distribution of those. So the distribution of the facular ones was pretty flat. There were some which didn't really show a correlation. Those are the black points. And, you know, they're kind of in between. That's good. But they also showed a fairly flat distribution. And the blue points, you know, peaked at between 10 and 15 days. And I think that maybe is okay. That might just be the sample that that Kepler was sort of biased towards. So I was less certain that that was a problem. And it, you know, the Montet et al. made a big point about the fact that it fell off on the long period side, and I just made the point, well, it also falls off on the short period side.
Mm-hmm.
You know, so we have a nice explanation for the long period side, but why does it fall off on the other side? You know, you would have thought those stars should just be more and more spot dominated as you go to short periods. So those were the two sort of issues I raised around the specular question.
Yeah.
And I think that's probably all I need to say about that. That's the essence of the paper. So it, you know, I've been in the very unpleasant position of sort of debunking stuff that people write, including my own stuff.
Oh, there we go. Well, that's fair enough.
About the more I understand these light curves, the less I necessarily believe what we said about them.
Okay.
That's you know. So I'm working on 2 papers now. This one to get more rotation periods, but also to check, you know, how many times are we blowing it with the double period versus the single period. And the other question is, and can we actually learn anything about faculae? Can we learn anything about differential rotation? Can we learn anything about star spot lifetimes? And right now, I'm not so sure about faculae, and I'm not so sure about differential rotation. I think that I agree we can learn something about spot lifetimes, but what has been done so far, I'm not so sure is fully correct. So that's what I'm doing these days. And I don't like writing papers saying, oh, you know, we're all wrong. Everything you know is wrong.
Yeah, those don't go over so well.
No, they don't go over so well. And so this paper, you know, has hardly any citations. I'm not surprised. And the next ones probably won't either, because they'll be sobering.
So let me ask then, what do you think it would take to say something more definitive? Is this something you can get out of tests, for example, or?
Yeah, you know, I wish we could. And
Plato?
So the problem with tests, the beauty of tests is they're doing full frame images all the time. And people haven't been absolutely calibrating test data yet, but there's no reason why they can't. And so I expect that will happen. The difficulty with tests is it's too short for the most part. The observing periods for most stars are, you know, a month. And I'm sure it would take nothing to convince you that if I took the data we've been looking at and only pulled out 1 month, some random month, I might reach any sort of conclusion. So
okay,
that's not helpful. There is the polar caps that TESS gets a whole year's data on. And maybe that's, at least for more rapidly rotating stars, maybe that's enough rotation periods to do something with. So there I'm cautiously optimistic that we might be able to do a better job of sort of testing this vacuolar signal, for example. We're working hard on trying to get differential rotation separated out from spot lifetime, because what my models show is they can get pretty entangled. But
so if
one possibility is maybe machine learning can help with this problem. I'm involved in a project this summer that will look at that. So I haven't given up, but it's harder than it looked. Let's say that.
So if you could wave your magic wand on observations that you could take that would resolve the situation, what would you do?
Well, I mean, if we could get absolutely calibrated photometric observations for 2 or 3 years, that would help a lot. It won't solve the degeneracy problem, but so in order to if I could wave my wand and put any spacecraft up there that I wanted, I would monitor the activity proxy, some other activity proxy at the same time. So, like for example, if you just looked at if you had a spacecraft with narrowband filters on and off the magnesium-2
Okay.
resonance lines,
Okay.
and you could tell, whether the star was more or less active, or X-rays, and then you could relate that to the photometric variability. And then if you watch for, long enough, you could disentangle all of this, I think. But the way it is right now, we don't have all the. There are a couple of possibilities that are still in the wind. While Kepler was up, a lot of people took spectra, especially the people who were doing radial velocity work on planets.
Right.
They typically have the calcium lines in their spectra, so that's something that could be pursued.
Yeah, right. I was going to ask if you could do enough follow-up on individual stars.
Yeah, well, I mean, people were following up the ones with planets.
Sure.
They took a bunch of spectra in order to get the radial velocity signal. So you can relate the spectrum. Each spectrum can be related to a Kepler photometric point, and you know what the star was doing around that. So that is just a matter of collecting up the data and putting it together.
Mm-hmm.
The data is already in the can. With tests, as I said, for the most part, you're not going to watch long enough to really matter. But maybe for the polar cap stars, you could do that as well.
Okay.
But the essential degeneracy between the light curves and the actual spot configurations is just going to be there, and so that'll stop us, at some level from really knowing what's going on. Now, the beauty was Kepler also saw a few cases where the planet, as it transited the star, went over spots. That takes care of all the degeneracies in a hurry. Oh yeah, there's a spot. There's a spot with this amount of brightness, and it's here on the star. And the planet comes around again, and there's a very, very nice case that just was published, Kepler 17, where the planet goes over the spots while they're still visible several times.
Oh,
so you can see them going.
Nice.
So there you can get a much better idea of whether they're growing or decaying or whatever. So that's another set of data that's of interest.
Cool. Well, while it may be a little degenerate now, it gives some nice targets to go after in the future. Now that you've laid out some of the what some of the core issues are.
Yeah.
So it's a clear path forward on getting the type of data that we need to resolve this. So it's very cool.
Well, what's great is all this great photometric data. We just need to learn how to extract as much information as we can from it.
Yeah, well, I think your AI project will be interesting on
that'll be interesting.
What it can help. So Gibor, I want to thank you so much for walking us through your lovely paper. I really appreciate it.
Well, I really appreciate the opportunity to talk about it with you.
Sure. And for those who would like, you can reach out to Gibor. We won't be putting his email address in a YouTube video or in a description, but those of you in the game will know how to find him. He's not hard to find, and we'll carry it on from there. So thank you everyone for attending, and we'll see you on the next one on the good stuff of the AAS Journal Author Series. Thanks. Bye-bye.
Thanks very much, Frank. And thanks for listening, the rest of you.